Butler Volmer model of electrode kinetics. In previous lecture, we have considered this redox reaction in which an oxidized form is reduced with the forward rate constant, and the reduced species was converted to oxidized with backward rate constant. And the expressions for the quantitative relationship between these two rate constants and the applied potential over the electrode is given as equation 9, which is describing the relationship between the forward rate constant and the applied potential, whereas the equation 10 is describing the relation of backward rate constant and the effect of applied potential. So here this Kf naught and Kb naught are the also constant which are independent of applied potential. It means that these rate constants are for equilibrium and at which the applied potential E is 0. Now again consider an equilibrium condition when the applied potential is 0. It means that the potential of the system is equal to equilibrium potential. So the difference of potential that is in the exponential form, it will equal to 0, and the exponential form is, for example, I'm taking question number 9. Here difference is 0. It means that we are taking the applied potential as equilibrium potential at equilibrium condition. So this term equal to the exponential power is 0. It means this term is equal to 1. For this case, the rate constant of forward reaction will be equal to the constant that is for equilibrium condition. Same condition can be applied to the question number 10. So we can derive the rate of backward reaction is equal to rate constant of backward reaction is equal to the Kb naught. So this constant is known as equilibrium constant, that is independent of the applied potential. So here in the reaction for the equilibrium condition, the rate of forward and rate of backward reactions are same, so these two constants are equal. So we can see that these all four constants are actually equal to K naught, which is known as equilibrium rate constant. For the electrode kinetics, this K naught is actually given the special name of standard rate constant. So using this rate constant, the equation number 9 and 10 are now redefined as equation number 11 and 12, as the rate of forward reaction is equal to product of standard rate constant and an exponential vector, which is depending on the applied potential. Similarly, for the backward rate constant, we have expression 1 minus alpha, which is known as transfer coefficient. So here E is applied potential and this one is equilibrium potential, and N is the number of electrons transferred during the redox process, whereas F is a factor which is equal to the Faraday rate constant over general gas constant into temperature. At the start of discussing the Butler Volmer model of electrode kinetics, we had shown the expression for the current measured at electrode is actually equal to the expression given here, in which here again we have two rate constants, whereas C naught is the concentration of oxidized species at the surface of electrode, as the distance of this species is 0 from the surface of the electrode. It means that this species is present at the surface and at respective time, whereas Cr is the concentration of the reduced form according to the example of redox reaction given here. And this current is actually difference of cathodic and anodic currents, which are based on the application of either positive or negative potentials applied to the electrode. So by comparing this equation with the equation number 11 and 12, we get another expression as current generated at the electrode is equal to the equilibrium rate constant and applied potential. Now we get equation number 13, and we can rearrange this equation as by taking this constant as common term, and this expression is same. So we get a final equation number 14. This relation is very important as it and a variation derived from this equation is used in the treatment of every problem requiring an account of heterogeneous kinetics. So here in this equation, K naught is an important constant, and the physical interpretation of K naught is straightforward. It's simply a measure of the kinetic facility of the redox couple.